I'm getting ready, so just be a moment. Question: are there extra tests for the homework? Oh yes, there are. Well, I suppose they will be withheld. Here. Oh, that's unfortunate. I forgot to upload the tests. Yeah. Okay. Well, you'll get to be graded on those tests, I suppose. All right. Let's get started. So hi everyone. So today we're back to the whiteboard, and we're going to just take a closer look at what this week's lab will be about. I haven't uploaded the assignment to Brightspace yet, but it's on the public repo, and let me think. Oh yeah, there probably should be some tests as well, so I'll go fix that for the tests here. And this program is going to be all about adding continuations to our metacircular interpreter. So the lab is called metacc because we're calling our current continuations current continuations. So this is the metacircular evaluator, but with continuations this time. And this one is pretty mind bending. So I just want to go through and basically talk a little bit about some of the stuff that we want to do when we are doing the metacircular evaluator in this situation. Do we have any questions before we get started? Okay, so this time the way the lab is structured is that most of our code isn't you're not going to write all of the interpreter. You're just going to write a few particular functions that are needed to do various things in the interpreter. So in the lab, the order is we're going to first do eval literal, then we're going to do eval return statement, and then we're going to do eval binary expression. Hang on a sec. We're going to do apply, eval throw statement, and eval try statement. And I think that's it for what we're going to do in the lab. So that's pretty cool. We'll look at some of these in the lecture today, but I also am interested in just showing you how the interpreter generally gets structured when we are, doing this situation where we have all the current continuations, and we want to continuationify our interpreter. So the way we're going to do this is I want to first take a look at eval expression, and we'll just see how eval expression looks different when we make it take continuations. So what we'll do first is I'm just going to write a non-continuationified version of eval expression with a few examples of the types of things we want to do. So we take an expr and an env, and then, you know, what did we do in the lab? We said, hey, what is my, sorry, just a moment. What is my expression type? And what are a few examples we're going to do? Let's try, you know, doing, you know, what if we have a literal? Well, we just returned whatever the literal was. I think it's literally called literal. Let me just check. Yeah, no, it's a value. And, you know, let's say that we had a binary expression. What did we do in that case? Well, we said, you know, do the bin op. And here eval bin op was just that helper function that took in whatever it was the binary function that you wanted to do was. And took in, then we wanted to first evaluate sub-expression. So eval expr left, and eval expression, I'll put this on the new line, eval expression xp right. And just for fun, let's also do logical expression. And so for this one, if you recall, we did something like, you know, we switched on the operator type. And if it was and, then we said, okay, well, return val expression xp left env and val expression exp right env. And the rest sort of proceeded in a similar way. And so what happened was that this and here took care of the short circuiting for us. Okay, so hopefully all of this looks fairly familiar. You had to do this for your lab. The lab was due today, so you know, should all be fresh in your mind. So how are we going to continuationify this? Well, to continuationify this code, we have to do the same thing that we did in lecture, which is we said that we were going to CPS the code. Where's my, just a sec. I don't know where my eraser is. Okay, fine. We'll just do this by hand. And what that means is we're going to take the code here and we're going to give it a new current continuation. Now let's do all of these in blue. So the current continuation says, hey, once we are done executing this expression, what should we do next, right? So for example, we need to get rid of all of these explicit return calls and we need to replace them with new calls. And we also have these calls to eval expression, which are going to cause us problems because, hey, a valid expression no longer returns, so I can't actually, pass in an expression. I have to go ahead and implement it myself. So let's just go ahead and do it. So the literal case where I'm just returning exp value, this shouldn't be too hard, right? So I just want to call the current continuation with the value that I wanted in the situation. And that's good enough. And let's look at the binary expression. Well, we also looked at a kind of similar situation in class, which is that, when we had some function calls, what was our plan? Our plan was to take our function calls and convert them for do one, right, and pass it a continuation that said what to do afterwards when we did the function call in question. And one of the rules I said was, if you're not sure how to CPS an expression like this, all we need to do is rewrite it into a bunch of variable bindings for all the intermediate computations, and then hopefully things are clear. So let's go ahead and write that version of the code off to the side. So instead of evaluating the expressions like as sub-expressions in the expression we have here, what we're going to do is we'll say, okay, what do we need to do first? We first need to evaluate the left. So var left equals val expression exp left end. So I'm not CPSing yet. I'm just rewriting this code in a form that makes it a little easier to see how we are going to go about CPSing it. So after I'm done evaluating the left sub-expression, I want to evaluate the right sub-expression. And then I can finally do well, let me just go ahead. Yeah, so let's suppose eval bin-off doesn't take a current continuation as an argument. So because we could do it that way, but I'm just going to cheat a little. So then all I need to do is return exp operator left, right. So hopefully you can see that this code and the code down here are equivalent. And so now let's CPS it. I'll delete this code down here. And so how are we going to CPS this? Well, a val expression no longer returns, and instead it takes a current continuation that says what to do next. So let's do that. So a val expression left. Sorry, not left. exp left. Give me a sec. I want to find where the toolbar went. Oh, here we go. There we go. Here it is. Okay. So val expression left and now in our glorious blue, we have a function. And what is this function going to get? Well, it's our callback, so it's going to get called with a result of evaluating the expression in the situation. Let's go ahead and move this guy down a little. Oops, I didn't want to do that. And what are we going to do after we've gotten the left value in the situation? Well, our lines of code say we want to eval expression again. And once again in our blue, what's going to happen when we call this function? Well, eventually we'll get a callback giving us the value for right. And then finally, we're going to return, but we're not actually going to return, right? We're going to call the current continuation, this guy, with whatever the result of putting these two primitive operations together. There's a question in chat. I'll get to you very shortly. And then let's close all of our braces. There we go. I think that's enough. So the question in chat is this triangle nested functions and callback considered bad style? Is there a way to do it without nesting? And the answer is, if we're doing it with functions, there's no way to do it without nesting. So yeah, it's going to look kind of bad. This is something that you have to solve on a programming language level. Arguably, what we are doing right now is writing that solution in the programming language, right? We've CPS'd our interpreter, but the user code, the user JavaScript, can stay blissfully ignorant of any of the stuff that needed to be done to make this happen. So that's pretty handy. One more thing that I want to point out is that how did you know that this guy didn't take a continuation? And honestly, that just totally depends on how you go about implementing your code, right? So we said eval expression takes a continuation, and we did it that way. And eval bin op, we could have said also took a continuation, and it wouldn't have taken us much longer to implement it in this way. But really, you just have to look at the documentation. Does the function take a continuation or not? And that'll tell you whether or not you have to CPS or not. So in this case, I said eval bin op wasn't taking a continuation. But if it was, then I would probably have to write my code like this. Eval bin op exp operator left, right. And then what do I need to do? Well, technically I need to create a new function, but because what I'm going to do with the result of eval bin op is immediately return it, I can just pass in the continuation directly. A bunch of squiggles here. Questions so far? So we are good for eval literal and eval, not eval return statement. We haven't done eval. And good for eval binary expression. Okay, there's a good top level question, which is why would we want to write our meta interpreter in continuation passing style? That's a great question. And we haven't gotten to the interesting part, right? So the transformations that I did here for literal and binary expression, they're very boring. They're sort of just the stuff we need to do to like plumb our current continuation on, but we haven't really used it in any interesting way. So the points where this will actually matter is when we want to implement throws and tries in our interpreter. There won't be an easy way of doing them without actually going ahead and re-implementing this by ourselves. Another reason you might want to CPSify your interpreter is because you want to add some control flow constructs that are not in your host language. For example, we could add call CC as a construct to our language. Actually, we'll do that right now. I'll show you how to add call CC. We could add call CC as a primitive function to our language now that we have this current continuation, and it would be pretty crazy, but it would work. And yeah, I mean, obviously you wouldn't be able to do that in stock JavaScript. So we had to re-implement our interpreter, and then we had to implement our interpreter in such a way that we actually had continuations available. There's another question, which is how can the interpreter we write in CPS fit into the bigger picture? Right now it is occupying too much stack, and we need to modify so many eval functions just because we want to support control flow. How does a real world interpreter deal with this issue? That's a great question. So let me see. Do I want to answer this now? I'll answer this now. So, okay. So there are a few issues here. So let's start with the easy one. So as you can see, what we've got here is we've got these function calls, and JavaScript is not a language with tail call optimization. So if we run our interpreter for too long, we will actually run out of stack space. So if you're in a situation like that and you want to not run out of stack space, you have a few options. So one option is you can use what's called a trampoline. So what's the idea behind a trampoline? So the problem was we ran out of stack space because we directly called into the continuations inside of our functions. So our stack keeps getting longer, larger, and larger because JavaScript doesn't tail call optimize. Notice that all these continuation calls, they're all in tail position. So it's not an us problem, it's a JavaScript problem. So instead of directly calling the continuation the trampoline transformation says, hey, what I will do is I will instead, by the way, you don't need to know this for the lab. This is just for fun. You can instead return the continuation you want to call as well as what you want to call it with. And this sort of breaks the rule that I said, which is when you CPS your code, you never ever call return. But the idea here is we're using the return to get rid of the stack frame that we were valuing right now, namely the eval expression stack frame. And then our trampoline, which is on the other end of the line, will see, hey, you returned this continuation and this function. So now this value. So now I'm going to go ahead and call that continuation with that value to continue executing on. So instead of having a call stack that looks like this, you have a call stack that goes back with the continuation, and then the trampoline, that's what we call this, goes ahead and makes the call again. So if you flip this upside down, this looks a lot like bouncing up and down a trampoline. So that's a pretty common trick if you're writing in a language that doesn't support tail call optimization. Now, in real interpreters, you'll probably be writing it in C, and you'll probably have some explicit representation of the stack, and you can just go ahead and set things up correctly so that you don't run into problems in this case. But this doesn't answer the other question, which is like how do real-world interpreters actually write control flow, right? That's a pretty interesting question because you can CPS your interpreter, but a lot of folks don't, in part because to actually pass around continuations, you need a host language that supports continuations. But as I mentioned in the previous lecture, there aren't that many languages that support. It's not your host language doesn't need to support continuations, but your host language needs to support closures. And if we're writing a metacircular interpreter, we're targeting JavaScript, and JavaScript has closures, so no problem. But if you're in a lower level interpreter situation, you probably don't have closures, so you're going to have to build that all yourself. And so the answer to this question is that you're probably in the business of explicitly representing the state of your program, the stacks of your program, and all that other state. So you don't actually have an honest to goodness function that you can just call, but all of the management of the stacks and the interpreter state on your virtual machine, morally what you're doing is you are manually implementing continuations, these closures, but they're being used as continuations and handling them in your function. So a common implementation technique when you're writing an interpreter is to write what's called a virtual machine. So you have a simplified language which doesn't have all the stuff in your surface language because you want to add a lot of convenient user features, but instead you just have a stripped down language, and then you have a virtual machine that just goes ahead and executes things on that machine, and it maintains state. And if you need to do non-local control flow, the virtual machine is responsible for figuring out how to restore or save the state to make these things happen. And you will basically be implementing something that's very similar in that situation. Does that answer the question? Cool. And there's a comment in the chat which I didn't know, which is that in ECMAScript 6 they're supposed to do TCO. So that's cool. And then this code, you don't even have to write a trampoline in this case. Let's see. So I do want to show y'all one particularly interesting case, which is the Anand operators. So we're actually going to get a little bit of payoff for the change we made. So what's going on here? So I said that binary expressions were they're not short-circuiting, and logical expressions are short-circuiting. So that if I evaluate an expression and I get some value, then and in the case of false, if it's false, then I skip evaluating the next expression. And we did this sort of cleverly in the old implementation by just using the old ampersand ampersand in the situation. But when we continuation passing transform a piece of code, we need to explicitly reify this act of short circuiting. So let me show you what this looks like. So I'm going to just assume that we're implementing ampersand ampersand logical and I'm going to skip the case statement here. So what do we say we're going to do when we evaluate ampersand ampersand? So what we're going to do is we're going to first evaluate the left subexpression. And it's going to call us back with the value of the left subexpression in this situation. And now we have a choice to make, right? So the choice to make we have now is that we could evaluate the right subexpression. We could also not evaluate the right subexpression. And whether or not we should do that depends entirely on whether or not this left is true or not. So if the left is true, that means it is profitable to continue evaluating the next expression. So we'll go ahead and eval expression exp right env, and then whatever this expression evaluates to, that's the final result we want in this situation. But if left is false, then there's nothing left to do. We don't need to actually evaluate the right subexpression. So we'll just bug out immediately and call the current continuation with the false value that was given to us by left. So what I just want to point out here is that continuation passing style makes it super explicit what exactly is going on, right? It says that, hey, first you evaluate this expression, and if it's true, then you evaluate the right expression. Otherwise, you don't. Like, you can just read this off, and it's a lot more explicit than the other case where, you know, if you weren't paying attention carefully, you might have, you know, glossed over the fact that we were using ampersand ampersand, and that was short-circuiting. We can also see now that we can play around with how we go about evaluating things, right? So for example, we could say, hey, I think left biased short circuiting is dumb, and I want to have right biased short circuiting in my language. And so what I can do is I can just swap which expression I evaluate first. Or I could say, I don't like short circuiting and I want it to not short circuit. And then what I would do is I would unconditionally evaluate the expression for both left and for right, and then do a logical operation on it. And you can see that, you know, there's a very straightforward code change to make for each of these cases. And I guess you might say, well, you know, ampersand ampersand is easy if you wanted to like switch the short circuiting order, you just swap the arguments. But, you know, imagine that it was some sort of function where, you know, it wasn't commutative and then it's still short circuited. Well, you could still figure out how to make it work in the code this way. So that's logical expressions. Any questions? And I'm going to get to another screen. Okay, so let's look at an actually interesting case where we actually are going to have call CC work for us. Wait. I promised that I would say how to implement call CC. So let's just go ahead and do that real quick. So let's just imagine we have some call CC expression. And what exactly is this expression going to have? Let's say that it has a let's say it has an exp, which is the thing we want to evaluate on the inside. So so how would I do this? Well, I've got my current continuation, so I just need to call the expression with the current continuation. So I'm going to evaluate this expression. Extending the environment to hold a binding for the current continuation. I don't know. Let's just say it's, you know, they gave us a name. And we give it the CC here. And what is it that we want to do when we're done? We return CC. And that's it, right? So we've done all of this work passing around this current continuation value. And as a result, we it's very easy to write call CC because we just pass the current continuation into the expression, you know, giving it some binding name so people can access it. Okay, that's enough for call CC. Okay, so there's a question which is, can you give an example of using call CC? I can't quite figure out how this function could be used and how call CC differs from CPS. Let's see. I got time. Okay, let's see. So, okay, this is an interesting exercise. So let's try implementing try catch with call CC. So, so in a stereotypical try catch implementation, we have a we have the try thing, which does a bunch of stuff. Maybe it throws, maybe it doesn't. And if you throw inside the try block, you get to the catch, and then you run some handler code in this situation. So if you didn't have native try catch in your programming language, it would be kind of difficult to write your code, simulate this language feature. Why is that the case? Well, how exactly would you implement throw, right? You need to somehow stop executing the current set of code and non-locally jump to some other point in the universe. And that's not so easy to do. If you're just a lowly, you know, surface level language implementer, programmer who doesn't have access to, you know, deep guts of your program. So let's see how call CC would let us actually do this. So in the call CC version that I wrote earlier, I'm gonna actually make this be a function this time. So what's going on here? So call CC says, give me a function, and I will give you the current continuation for this. So if you call CC at some point inside the body of this function, I will immediately stop executing whatever it was that I was executing and start executing whatever the continuation was. In this case, the continuation is, you know, whatever the rest of the program was doing after the call CC call. So how exactly can I use this to my advantage? Well, we can see that, hey, you know, this is pretty handy because it lets us kind of do this short-circuiting behavior that I was looking for with throw. So let's see how we can go about doing this. So what I want to do is I want to write my body of my function body of my function, and then I want to call CC somewhere in the middle to do the throw, right, with my exception body. Now, there's something a little difficult. So one is that I need to somehow get at this current continuation, even if this is, say, nested inside of a function, right? So we talked about how exception scoping is similar to dynamic scoping for variables. So if I had dynamically scoped variables, I could just go shove CC in a dynamically scoped variable and then access it later. Absent that, I just need to make sure I pass around CC around so that I eventually get here. But there's one more thing that I need to do, right? So this CC will just dump me unceremoniously outside of the function. But I don't want to do that. I want to run the handler first in the situation. So I don't actually want to call the current continuation. I want to call something that I'm going to call the failure continuation. And for those of you who are wondering why I'm off on this tangent, this discussion about failure continuations will become very, very useful when we actually go and try to implement a vowel throw statement. So let's call this a catch continuation. There's a question in chat which is, isn't CC the current continuation we are looking for? So CC is the current continuation for the call CC call. So let me just put a little function call over here, foo. So if I call CC, I won't bother running the handler. Well, I haven't put the handler anywhere in this program. And I'll go straight to the outside of call CC, which will give me foo. So that's not exactly the same thing as a try-catch block. With a try-catch block, when I throw, I need to first run the handler, and then I can go ahead and keep running the rest of my code. So I'm going to introduce a catch continuation. So what is this continuation going to do? Well, hang on. So what this continuation is going to do is it's going to be given an exception, and then it's going to run the handler, and then it's going to bug out using the current continuation, right? So all I'm doing is I'm saying, well, before you bug out with the current continuation, please run a bunch of handler code and then go there. And now inside my body, when I throw, I'm not going to call the current continuation. I'm just going to call the catch continuation with the exception that I want to throw. And so what will happen? Well, catch CC is just a normal function. So I'll hit this function, run the handler, then hit the current continuation, and that'll bat me straight out to the outside of the function. Does this make sense? One thing that I'll point out here is these look very similar, right? So in the case of the exception, I used throw to get a non-local control flow jump. And with call CC, I also used CC to do a non-local jump to the outside of the function. Actually, this correspondence is pretty useful. So in languages that don't have continuations, you can implement one-shot continuations. That is to say, continuations that can only be called once, using exceptions. Because you basically say, okay, when you're done, throw an exception, and then the handler will catch it and then resume execution. Of course, exceptions are not as flexible as continuations because, for example, at some later point in time, I could call the continuation that was passed into call CC again and warp back to this point in time. And that's pretty crazy, and you have to make sure you actually implement support for that in your language runtime. Any more questions? So remember this, because we're going to do the same thing when we are modifying our interpreter. So let's go ahead and try modifying our interpreter now. Let me save first. All right, so where shall we start? So let's first talk a little bit about eval statements, which I've never done in lecture, but I mean, it's pretty boring, to be honest. So eval statement, it's a function which takes in a statement, an environment, and I'm going to go ahead and also say, hey, we've got the current continuation, and we've got what I'm going to call a continuation environment. What's a continuation environment? Well, that's just it's just a dictionary that has a bunch of continuations in it. So like that catch continuation, that'll be an entry in the environment here. And we have a bunch of possible statements. And some of the important statements that we have are, the try statement. And the return statement. And more ordinary and boring statements like expression statements. What's an expression statement? Well, that's just a bare expression that, is in a statement context. So like if you do a function call, that's going to be an expression statement to the function call in question. So like expression statement, right? We already said how to evaluate expressions, and we're just going to go ahead and do that, and it's going to be very normal. And then, what do we do when we're done? Well, we just call whatever the concurrent continuation was for the statement itself. And no funny business is going to happen with a continuation environment, right? This is normal, nice and easy, whatever. So I'm just going to go ahead and delete this because we don't need to talk about it. Now, previously, when we implemented return statement, we said that we simply just returned the result of evaluating the expression that was in the return statement. Let me just check what it's called. It's argument. So argument is the expression that is in the return statement, and we just did this, right? So one of the limitations in the previous lab was I said, hey, return statements don't short circuit, right? So if I had a function and I said return 2 and then return 3, and your old interpreter would have done was it would have said, okay, well, return 2. So we evaluate that statement and we return 2, and then we would just march on to the next statement and say return 3 in this case. So now that we have continuations, we can fix this, right? So the goal is we're not just going to translate this into a call into CC, because that would be wrong, right? CC is saying, hey, go do whatever is the normal continuation from the expression. We want to short circuit. We want to short circuit in the same way we short circuited with logic expressions. We want to say, oh, don't bother with that. Just go straight to the the previous stack frame that had called this function in the first place. To do that, we need to actually know what the continuation for that frame was, and to actually get that, we have to have actually saved that continuation somewhere. So I'm just going to posit without proof, because we haven't implemented this part, that this environment, this continuation environment, contains a return continuation. And that return continuation is going to be like the current continuation, but instead of going to the next line, it's just going to go to the function that called us in that situation. And so now it's not too hard to finish off this expression. So we're going to go ahead and evaluate the argument expression, because, you know, that's just what we need to do. But once we're done, right, we're not going to put in CC. That would be wrong. We're going to put in the return continuation. And so when exactly do we set up these return continuations? Well, actually, we need to go back to a vowel expression. So in a vowel expression, we evaluate a function, right? So when we evaluate a function, namely when we apply a function, we're going to do a bunch of stuff, and this apply is going to have a current continuation, right? So what did we do? We extended the environment. And then what we wanted to do was we wanted to eval the statements inside the body of the function. And certainly when this function returns, it's just going to return with a normal current continuation. But the return continuation needs to get updated, right? What we need to do is we need to set a kenv that's new. And this kenv points its return entry to point to the current continuation at the time we ran apply, right? Because the current continuation at the time we run apply is what we're going to do after this function returns. So what's going on is that we've got a bunch of continuations, right? We have the current continuation, which changes as we execute our program to say what we're going to do next. But as we do various control flow constructs that change the meaning, change where control flow should go when they are invoked, we also need to go update the continuation environment to point to the correct new locations. Questions about this? And so we are done with return statement and apply. It's a question, which is, in JavaScript, is there any difference between writing kenv square brackets catch and kenv.catch? Don't quote me on this, but I believe they are the same thing. So you can write them whichever way you want. Another dumb JavaScript thing just to watch out for. Kenv is mutable, so you might be tempted to say kenv return equals cc, but please don't do that, because once you return from this function, you need to restore the kenv to what it was before, so that if someone calls return in the outer function, you return to the correct place. So just allocate a new kenv. That's an easier way to go about doing things. Okay, so let's look at the final part, namely a val throw statement, a val try statement. So, sorry, I didn't want to delete all this. So let's do things in the opposite order. So let's do try statement first. So what are we doing when we evaluate a try statement? So let's just go ahead and remind ourselves, right? So a try block has two parts, and what we're going to do is we're going to have, we'll call this body. So this part of the program is going to be statement body. And then this part of the program is going to be statement handler body. And this part will be statement handler param name. That's just how the syntax tree goes, right? So, or what we want to do is we want to do something like, you know, eval statements statement body with the same environment and mumble something with the kenv, and then with this good old-fashioned current continuation, right? So what this is saying is that, hey, when I hit a try catch block, I want to go and start off executing all the statements in the body, and then if they all finish without any problems, I just want to go ahead and continue on doing whatever it was that I was doing before I call the statement. So what exactly should I put here? Well, I need to update my kenv so that I have a updated cache continuation that handles the handler, right? This is what we did in that example we did earlier with call cc. Let me give myself some more space. Oops, didn't mean to do that. So my kenv is some dictionary, and we'll just go ahead, and the return continuation doesn't change. That's the continuation we were just talking about, right? Because if I return from a try block, I go and find wherever it was the boundary of the function that I'm in was. So, you know, I still want that continuation. Nothing changes there. But when I throw, or let's call it catch, that's the way we're naming it in the lab, I want to do something else. Right? I want to run my handler. Let me give myself a little more room. Statement handler. Some new environment, right? So I'm not going to fill this in, but what I need to do is I was given an exception, so I need to put it into the regular environment so that code inside of this statement handler can access it. And I need to run this with some continuation and some current continuation, and also some continuation environment. So let's first think about what the current continuation should be. So after I'm done handling the catch statement, I just want to go ahead and do whatever it was I've recovered, right? I didn't actually do anything else. So I want to go ahead and use the normal current continuation in the situation. For the continuation environment, that's a little trickier to say. In particular, what should happen if I return from the body, or if I throw an exception inside the catch block? That's a question for y'all. What should I do if I return? Yeah, I should call K and return. And if I throw, what I should do? Well, I should, throw to whatever the ambient catch handler was, at this top level. So actually, I just want to use the original continuation environment as is without any modifications. So that's the implementation for try. And now if I want to throw, well, hey, let's take a look. So throwing has an argument. So I need to evaluate that argument first. Doing some object allocations or whatever. And the current environment. Using the continuation environment as we'd expect, because if we throw an exception while we are evaluating the exception we want to throw, we're still going to throw an exception to the ambient handler in the context. The difference, though, is we're not going to continue on as normal. We are going to continue on to the catch continuation, which hopefully we had installed when we wrote this function here. Questions, comments? So let's mix this up a bit then. So now what we're going to do is we're going to make this a little more complicated. So this was the case when we had try and catch. But in lecture, we also talked about a third construct called finally, right? And what finally said was when we are done, we want to always run the code in finally without no matter what, right? So if I return from the try or if I throw out of the try, and then when I'm done with the handler, I return normally, or I return out of the handler, or I raise an exception out of the handler, I still call the finally code and then do something else with it. So we're going to need to adjust this code to handle this situation. Okay, so what is this going to look like? So let's first start off by like sort of editing stuff and see how it goes. So we're starting off here, and one of the things we need to do is when we are done executing the code normally without any errors, I need to go ahead and run the finalizer, right? So what's going to happen, right, is I evaluate the body. If all goes well, I'm going to call the current continuation, but I don't want to call the current continuation. I want to, call the finalizer and then call the current continuation. So I don't want to have to keep repeatedly writing the finalizer logic. So I'm just going to say, let's say that we have some code. It's not letting me delete this. Let's just say that we have some logic called wrap finalizer. And all that does is it says, hey, give me a continuation. And what I'll do is I'll first run the finalizer. And then I will call your current continuation after I'm done calling the finalizer, right? So this gets us the code path that happens when I go in the try block, and then I exit. Fine. And then I want to do it finally, and then exit. Okay? So let's consider some other situations. So what if I am inside my try block and then I return? Right? So if I return, I sort of warp out and go to whatever the return, whatever the parent stack frame was. I'll just make this a little r in that case. So if that happens, I want to go to the finally block and then do whatever the parent function was. So to do that, I need to also modify my return continuation so that it goes through the finalizer first before I do anything else. So let's do this. Wrap finalizer doing a lot of work for us here. All right, so we've got the return case. So we've got our success cases going. We got nothing bad happened, and we've also got hey, you returned, you short-circuited out of the try-catch block. We should still run finally in that case. So now let's take a look at our error conditions. So error condition 1 is when I go to my try-catch block, I throw an exception going to the catch block, and then the catch block finishes processing normally. Well, once the catch block finishes processing normally, I should hit the finally block because I'm done and I'm just recovering out from here. So where does this correspond here? So I run my my statement body, I hit the catch continuation, and then I get through the handler without any exceptions, and that's going to get me to this current continuation. So hey, let's just go ahead and wrap that one too. Okay, so we've gone ahead and handled the success case, but there's another case that can happen when I'm here, which is that I could throw an exception inside of the catch handler. If I throw an exception inside of the catch handler, I will raise that exception to outer blocks, but not before I first run the finalizer, and then I go my merry way, right? So what path do I take in this code when I raise an exception in that case? Well, I hit my try statement, I evaluate my body, that goes to the catch handler, I'm evaluating the statements there, and then if it throws, that's going to hit whatever the value inside the continuation environment I pass in this case is. So I can't just pass a stock continuation environment, I need to pass something else. There's a question in chat, which is, could wrap finalizer be something like call CC, function CC, a vowel statement, statement finalizer, and KMCC? Yes, but you don't need the call CC. You're just passing in the continuation, and then you run the statement finalizer, and then go on to the continuation. Yep. So if I'm in the catch block and I raise another exception, well, hey, I need to wrap finalizer. And what do I put here? Question for the class. What do I put here? Do I put CC? That's what I've been doing all these other cases. So what would my code do if I put CC in this situation? So I get in my try block, it throw an exception, go into my catch block. My catch block would throw an exception, so I would go to my catch handler. The catch handler was wrapped with a finalizer, so I'd run my finalizer, and then I would call the current continuation. What's the current continuation again? That's the normal success case. But that's wrong. If I throw an exception inside the catch handler, I need to keep propagating that exception when I'm done. So I don't want to pass in CC here. I want to pass in the ambient catch handler in the context. And that kind of makes sense, right? Because previously we were passing in keenv, and keenv catch is the ambient catch handler. So I still want to run that. I just want to run the finalizer first before I do that. This record is looking a bit empty. So, hey, you know, we also have to handle the return case, right? And same deal. If I return inside the catch handler, I need to first run the finalizer, and then I can go ahead with return. Are we done? Well, whether or not we are done or not depends on how many continuations, how many ways to escape from the control flow scope there are. So far we've talked about returning, we've talked about throwing, and we've talked about the normal success case, right? CC. So we've checked all of them, right? So return, catch, and current success, and then return, catch, success. So we've handled all these cases. We're also going to execute the finalizer, but once we're at the finally block, there's no more finally block. If the finally block raises an exception, whatever, we're just going to raise the exception to the ambient environment. So yeah, we're done. But if you say, for example, wanted to add looping, so like you could have a while loop here, and maybe you could break out of the catch block. Well, you'd also need to handle applying the finalizer in those situations as well. So, you know, it just depends on all the ways you can exit control from your code. And as you can see, there's actually a lot of ways to exit control in a modern programming language. So it's pretty difficult to like catch them all. And that's why, you know, you're recommended to use something like finally so you don't miss any of them. Or if you're in a language that doesn't have finally, like C++, you're recommended to, you know, use RAII, which does the same thing because objects have to get destructed no matter how you exit scope. There's a question which is, does keenv only constrain entries of continuations that can exit control? I mean, sort of definitionally, keenv is all about non-local control transfer. So yeah, anything that can, you know, do something different than the current continuation, that's where you'd put it. One more thing that I'll point out is that catch is dynamically scoped, right? So when I apply, I have to pass on catch to the inside. But return and say break and continue, those are scoped to the function, right? So they get reset when you call into a new function. Any more questions? Any questions from Twitch? Okay, so I'll wrap up this lecture with just some final words about continuations. So we talked a bit earlier about like if you were implementing an interpreter, how would you go about doing things, right? And I said, hey, you know, if you're actually implementing an interpreter, you're probably working in a language where you have to, you know, implement closures and stuff and stacks all by yourself. So you're like responsible for dealing with that sort of thing. But most of the time, when you're writing code, you're not dealing with all of that stuff, right? You're like working in a reasonably high-level language that gives you a bunch of capabilities, and you can use those capabilities as you need. And so writing code in continuation passing style might still be a useful thing to do in certain situations. For example, if you need to do some sort of crazy control flow that your language doesn't natively support. This is sort of the moral of the story Knuth had when he wrote, hey, goto is useful in certain situations. Yeah, goto is useful because sometimes there are certain patterns of computation where the most straightforward way to express them is by actually having restricted control flow. So hopefully you'll never be in a situation where you need to manually write out continuations. But hey, if you ever are in a situation where you do need to, you now know how to do it. And of course, if you're writing in a language with lots of callbacks, well, it sucks to be you, but you're probably going to be writing this code all over the place because that's basically what callbacks are. They're continuations. Okay, that's everything for today. I'll see you all on Wednesday.